All right, finally in our measurements in science, we're going to talk about percent error. You may remember in the previous section on accuracy and precision, I made the comment that sometimes precision can feel like it's an opinion, and science is not really concerned with opinions. It's really concerned about data that can support something that we believe. And so we shouldn't be able to look at something and have differences of opinion about whether or not they are accurate or precise, and we do, and it's called percent error. Percent error is a formula that allows us to compare our measurements, our estimated or approximate values, to something that is the target value and see how close we got. And so then we can see what our percent error rate was. How close were we? Now, probably the easiest way to start introducing this topic is to do it in terms of taking a test. Everybody has taken a test at this point. And so we can determine what your error rate, your percent error on a test rate is, and then extrapolate from there. Percent error has the following formula. It is the absolute value of the approximate or measured value minus the exact or the target value divided by that exact value times 100. Okay? So what does that mean as far as a test? Well, if I'm taking a test, the approximate value is my test score, right? And the exact value is, what are the points that it could be worth? Well, it's 100, right? So every time you take a test, your target is 100 points. That's accurate. If you were the most accurate, you would have 100. We would go out from there. So let's say that you took a test and that you scored an 87. We can now calculate your percent error because we know what the exact value is and we know what your measured value is. All we have to do is plop it into this formula. We would take the approximate or your value, which is an 87. We would subtract the exact value, or 100, because that's how many points the test was worth. We would divide it by the exact value, which is 100. And then the step almost everybody forgets is you have to multiply by 100 to get it into a percent. Before we do any solving here at all, I want you to notice something. 87 minus 100 is going to give us a negative 13. But notice we have that in absolute value symbols. Sometimes it's nice to see this negative number, and that is a tell to you that you were short of the target. Because sometimes we can overreach the target and go well beyond the target. If you remember in the density example, the target value was 8.94 grams, and student 1 had one of the measurements that was 9.4, way overshot the target, had another value that was 7.3, which was way under the target. Okay? We'll take the absolute value of that 13, so 13 divided by 100 times 100 is going to give us 13%. We had, or you had, a 13% error rate on your test, right? 87 minus 13 or plus 13 gets you back to 100. On a test, a 13% error rate on a chemistry test is not too bad. However, 13% error rate in brain surgery could be the difference between life and death. So it's important to know with these percent errors is what's an acceptable amount of error. So not only will you probably need to calculate this, but then compare that value to one that would be acceptable or not. Let's work a couple other examples. We have a student here that measures the mass and volume of a substance and calculates its density to be 1.4 grams. The correct or accepted value is 1.3. So again, we need to decide what is approximate and what is exact. Whatever the student measures is the approximate. So that is 1.40 grams per milliliter. And to just make the point we had about certainty and uncertainty in measurements, because the 1.40 is a student measurement, the student is certain about 1.4. They are estimating the 0. But in the exact value, which is the 1.30 grams per milliliter, the 0 in 1.30 is not uncertain. It is exact. Right? So what is the student's percent error? Well, clearly we can see, since their measurement is more than the target, that we would have a positive value in this formula. So we have A minus E, absolute value, E times 100, and we substitute things in. The measured value, what the student got, is 1.4 minus 1.3. We're going to take the absolute value of that. We're going to divide it by 1.3 and divide by 100. So we're going to wind up with, grabbing the handy-dandy calculator, 0.1, 1.4 minus 1.3 is 0.1, divided by 1.3 times 100, and this student has a 7.7% error rate. One final example. What is the percent error for a mass measurement of 17.7 grams given that the correct value is 21.2? Well, again, we have to identify what approximate and what an exact are. The student measurement will always be the approximate value, so that's 17.7 grams, which means 21.2 grams is the exact. Now we can calculate the percent error. It is the approximate minus exact, absolute value of that, divided by exact, times 100. And then we just substitute in 17.7 minus 21.2. Now, before I even take the absolute value of that, you can see this number is negative, meaning this student was far below the target and not above. Again, that doesn't mean anything other than knowing you were above and below, because a percent error will always be reported in positive terms. 17.7 minus 21.2 equals negative 3.5. We take the absolute value of that, and it's 3.5. Divide by 21.2, and then don't forget to multiply by 100. This student's error rate is 16.5%. Refer back to this video as often as you need to complete the short worksheet on percent error.